So say you've got two resistors in your circuit and you want to find the equivalent resistance. Well, then you have to look and say, are these guys in series? Or are they in parallel? Because if they're in series, that means you've got them hooked up like this. So you got R1 and R2, and if the current goes through R1, it also has to go through R2. So first thing to note is in series, current is the same. And then if you want to find the voltage across them both, so that would be the total voltage drop here, well, the voltage across the whole thing is going to be the voltage drop across the first resistor plus the voltage drop across the second resistor. So the current's the same, but the voltages add. So my total voltage here is going to be my voltage drop across the first resistor plus my voltage drop across the second resistor. And what are those in terms of the resistance? Well, from Ohm's law, I know that my voltage drop across resistor is the current times the resistor. So the voltage drop across the first one, well, that's going to be my current through the first one times my resistance of the first one. And similar for the second one, that's going to be my current through the second resistor times the resistance of the second resistor. But the current's the same because, again, got to have conservation of charge. If the current travels through one, well, the charges don't have any choice but to keep going through the second. So we don't actually need these subscripts on these currents. And then my total voltage drop here, well, that's going to be my current through the whole thing, and then my total resistance, whatever this is. Because, you know, even if it's two resistors, that's still acting like something with resistance, so we can still use Ohm's law. And then I see I've got current times resistance, current times resistance, current times resistance. I can divide out current. So if I'm in series, my total resistance is the sum of the two individual resistances. So let me label that a little better. In series, I just add up my resistances, and that's how you add resistors in series. Now, on the other hand, if I'm in parallel, that's where, like, I had a circuit and then I split it into two branches, and I put a resistor here, and then I put a second resistor there, and then I brought the two branches back together and let the current go on. Now here, where I had the same current all the way through, when I get here, I have some current coming in, but then it can choose. It can go through resistor 2 over here, or it can pick resistor 1 over there. And then at the end, the two currents have to come together again. And so I'll have my total current all together. And up here, before it went in, that was the total current, and then it split up. So unlike in series, where the current's the same and the voltage adds, in parallel, the voltage is the same, but the current adds. So, and how do I know the voltage is the same? Well, that's a wire up here, this whole T thing. That's a wire, it's metal, it's a conductor. It's an equipotential. It's the same potential everywhere on this wire, all the way down to where it hits these two resistors. Same thing down here. This is a wire. Wires are metal, metal conductors. Conductors are equipotential. So we got the same potential all the way up to the bottom of the resistors. So the potential difference, top to bottom on the resistors, got to be the same. The potential is the same for stuff in parallel. The current adds because, like I said, however much current you've got coming in, when it hits this junction, it has to go this way or that way, and then it has to join up again, add up. So the total current is going to be the current going through resistor 1 plus the current going through resistor 2. And then from Ohm's law again, I can say, all right, current is equal to the voltage drop across the resistor over the resistance of the resistor. So the current going through 1 is going to be the voltage drop across 1 over the resistance of 1, and current through 2 is going to be the voltage drop of 2 divided by the resistance of 2, and then the total is going to be the total voltage drop over the total resistance, but the voltage is the same everywhere. Top to bottom, everybody is sharing a wire on the top and the bottom, so the potential difference has got to be the same. So we can get rid of the subscripts, and then we can say, oh, well, everybody's got V. Let's divide out by V. That'll become 1 over the total resistance equals 1 over resistor 1 plus 1 over resistor 2. And that's how you add resistors in parallel. Alright, so just knowing that things in series have the same current, but you have to add the voltages to get the total voltage, gives you this is how resistors add when they're in series. Whereas in parallel, their voltage is the same, but the total current will split up, and you have to add up the currents to get that, the total, and so that's how resistors in parallel add. Now it turns out you can do the same kind of reasoning to get the capacitance. So let's try that out. In series, so that is you have a capacitor and a capacitor just lined up like this. Things that are the same. Well, the current's the same. But current, of course, is the change in charge over time. So if we want to go the other way, the charge would be the integral of the current. So that actually means for a capacitor, we don't care so much about current as we do about charge. So if the current's the same, and obviously the time has to be the same because they're existing together in the same time, what this actually means is the charge on the two plates is the same. But then if we want to know the total voltage, top to bottom, the voltages, they add. And we also need to know the capacitance is Q over V. All right, so then knowing that, the total voltage over these two capacitors is going to be the voltage over capacitor 1. I'll call that guy capacitor 1, this one capacitor 2. And the voltage over capacitor 2. Rearrange this so we get Q over C is our voltage. So the total voltage is the total charge over the total capacitance equals Q on capacitor 1 over C of capacitor 1 plus Q of capacitor 2 over the capacitance of capacitor 2. But the Q's are the same. And I did this really quick with current, but let's just see why this makes sense. Alright, so if we have current coming down and we put on some positive charge on this top plate because we're feeding current in, well, that means we're going to have negative charge here, but that's going to happen because the positive charge left and went down to this next plate here, and of course it'll be just as much positive charge as left up here, so those two magnitudes will be the same, and then we'll have negative Q down here. So you see Q, the magnitude of Q is the same all the way through. All of these Q's are the same, so we can get rid of the subscripts. There we go, and we got Q, 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 and Q. Divide out by Q. And for capacitors in series, so we'll replace that total with a series, that is how you add the capacitance. Whereas in parallel, let me just sort of divide that up. In parallel, we had a wire, and we split it up into two branches, and then we join them up again down here. So we got capacitor 2 there, capacitor 1 here, and now instead of Q being the same and the voltage adding, when you're in parallel, the voltage is the same, but Q adds, and that's just because when you've got your current, and it comes down, it has to decide, do I want to go over here, or shall I split up and go that way? And however much current shows up, some of it will go on this plate, and all the rest of it will go over here. So if you want to know the total current, well, that's going to be the current on 1 sorry, the total charge, that'll be the charge on capacitor 1 plus the charge on capacitor 2. And rearranging what capacitance means, well, that's going to be voltage times the capacitor. So we can go ahead and replace that. The total voltage times the total capacitance equals the voltage on 1 times the capacitance of 1 plus the voltage on 2 times the capacitance 2. But voltage is the same for things that are in parallel, so we can just divide out the voltage. And then we'll get the total capacitance for things in parallel is just the sum of the two capacitances.